we've also been working hard to introduce these changes in AutoPIPE without heavy modifications to the input or output. So you, the designer, will be able to use these. We'll be able to use this analysis engine um, without much additional effort or learning.
So we got a question, Josh, about where does the experimental data come from where they came up with these equations for B31J?
Right. So the experimental data comes from. Uh, all I know is what it's actually used for is the generalized components that are supported with B31. I'm not specifically sure of where the experimental data itself came from, unfortunately, but I can get back to you with that as soon as I find out.
Also got a question, when do we expect ASME to incorporate B31J? And the answer to that is, we're waiting as much as everybody else is to get the, when the code will be released. I think they're in the final stages of that, but, nobody can be sure except for ASME themselves.
Yeah, B31J is currently a standalone code. I mean, it is part of the B31 suite. I presume what you mean is to actually be incorporated directly into the B31.1 or B31.3 codes. Um, but yeah, as for that, we don't know. But the B31.1 and B31.3 codes do reference this as an alternative, so it is available to you for that. Okay, so we were on the topic of stress intensification factors. So to save time, I'm only going to discuss one SIF equation for the welded T's. Each component itself, however, has three sets of equations, or has its own set of equations in each of the three directions, the in-plane, the out-plane, and the torsional. In terms of the T evaluation, branch legs have their own values independent of the header, which was not previously available in the B31 codes. So you can see here as an example in this table, the B31.3 column has one calculation for both the header and the branch, and now B31J actually has empirical extracted data that focuses on both the header and the branch independently. Now, I chose the welding T or T components in general for stress intensification equation example for a specific reason. I want to mention a special consideration that was put into B31J in the 2015 edition, that the geometry of the branch stress intensification factors will be applied to the location independent or dependent on the image shown here at the bottom. And the location of the stresses actually depends on the geometry, the relationship of the geometry between the bend and the header, or the branch and the header. Now this includes a d over 2 node, which would be placed here at the d over 2 of the header. But AutoPIPE will not be reporting that as a separate node in order to, at this time, simplify the actual evaluation of this. AutoPIPE will be evaluating the stresses at the appropriate location by placing a rigid link between these two if needed, based on the actual geometrical requirements. It will still be reporting the T-intersect on the branch side, but will be reporting the stresses at the appropriate location. I hope that makes sense. It's a little confusing. Yeah. So one of the things that I've mentioned is torsional SIFs. Although B31.3, ASME B31.3 has had torsional SIF considerations in sustained expansion and occasional stress for some time, AutoPIPE would always previously use a value of 1, and unfortunately would not give the users options to modify the torsional SIF for the stress calculations. With the introduction of B31J, AutoPIPE will support torsional SIF values other than 1 for the B31.3 stress calculations. Now it extends beyond this feature, that the designers will be able to, the designers will be able to enter torsional SIF values even in non-B31J models. So if you're using B31.3 without B31J, you will be able to enter user-defined torsional SIF values. Okay, unfortunately that was sort of a really quick run through for stress intensification calculations. Now let's look into flexibility factors. Firstly, only T components are affected by the updated flexibility factors in B31J. T factors themselves are evaluated using static analysis for each T in the model. During our main static analysis system processor, we actually restructure the stiffness matrices, and I'll get to that in a moment. The flexibility factors themselves are based on T geometry and joint definitions. And as the same with the SIF calculations, branch flexibility values are now independent of the header. Also, all of these factors, the T flexibility factors that are evaluated in AutoPIPE, will be reported as their actual factors in the model input listing, and the code compliance will reflect the changes in the stress reports. And I'll show that in an example demonstration here shortly. So here's an example of T flexibility factors for both the run and the branch leg of a welding T per ASME B16.9. So each T will produce 6 independent flexibility factors, 1 for each direction, in plane, out plane, and torsional, and 1 for each leg, or 1 for the header and 1 for the branch. By the way, does anybody know what the flexibility factors for T's in the existing B31 code is? It's a value of 1. So B31.3 is currently restricting the T flexibility factors to a very simple value. And what this code aims to do is provide more detailed flexibility analysis. Remember, the idea behind this flexibility analysis is to use more realistic flexibility factors based on the observations of the empirical, experimental, and detailed FEA data. So even after the flexibilities are determined, after they've been evaluated based on the geometry and the parameters provided by the designer, there are additional considerations that B31J mandates. And here are a few listed. Now, AutoPIPE will automatically handle all of these rules and all these considerations without any intervention from the designer. There are many others besides this, and I'm not going to go into them because there are quite a few of them. We'd be here all day. So these are just some examples, and we'll go over them a little bit more. We'll go over some of the considerations a little bit more in a bit. So that's pretty much the SIF and flexibility calculations. For our next section, we will be covering how AutoPIPE actually uses B31J analysis and how you can unlock the potential of this feature with minimal effort. So SIFs are applied to AutoPIPE B31J models in the same fashion that they are for non-B31J models, as I had mentioned previously. Definitions are provided in the preprocessor, and they are applied to the nominal stresses in the postprocessor. The requirements for T's and reducers, the inputs that are specific to B31J are added as well. And these SIF values, the resultant SIF values that are calculated by B31J are reported in both the model input listing and the code compliance, as well as the input grid. So here I have just a flow chart to sort of show how simple this is. The definitions are defined, the definitions and geometry are defined by the designer. AutoPIPE evaluates the SIF equations, and the code compliance evaluation and reporting is done. A similar approach here for T flexibility inputs. Geometry and component definitions are provided by the designer, and applied to the stiffness matrix analytically. New parameter fields have been added for each type, for each T-type. And the K-factors are reported back to the user with a new model input listing and report that I will show shortly. Again, a very simple flowchart to show you how simple it can be done. So now I want to talk a little bit about how we analyze, getting a little bit more technical here, how we actually analyze the flexibility factors. Evaluation and application of flexibility factors in AutoPIPE are a little bit more complicated than the SIF calculations. In the first image here, there is a generalized schematic of how B31JT is represented analytically by AutoPIPE. You can see that we have 3 load displacement elements, 1 for each leg, represented by these gaps here. If we were to zoom into one of these elements and look at it specifically, in the bottom left, we can see that although this rotational spring has no definite length, it does impose a rotational stiffness. This rotational stiffness is evaluated by using the stiffness equations to the right, and you can also note the flexibility factors. So once the flexibility factors are calculated by the B31J analysis engine, it's applied it creates its own stiffness matrix for each of these load displacement elements using those equations. So now the easiest way to apply, after we actually have our flexible joints, our rotational springs that are to be applied to the model, the easiest way to imagine this or to simulate it in AutoPIPE would be to introduce a flexible joint at the appropriate location for each leg of the T in the model. Now, each joint requires 2 nodes, one at the beginning and one at the end, to represent the length, and the actual flexible joint itself with the flexibility factors applied. Now you can easily imagine that for each T, we're going to have 3 flexible joints requiring 2 nodes each. So that's going to be a total of 6 nodes and 3 flexible joints applied to each T. If you were to, you can easily imagine if you had a model with a dozen or more T's, how exponentially complicated the model will become. Instead, AutoPIPE introduces the spring through a concept called matrix condensation, which creates an equivalent stiffness matrix of the actual pipe leg. Now it incorporates this joint, and I'm not going to go into sort of the nitty-gritty of how these matrix condensation is performed, but you can review the procedure in the reference posted at the bottom of the slide. Ultimately, the end result of this analysis is a slightly modified stiffness matrix for each leg of the T that includes this rotational spring, and actually incorporates and introduces this B31J flexibility. No additional nodes are created in your model. There's no additional complexity added to the model. So far we've looked at how SIFs are applied to the model, how flexibility factors are applied to the model. I do want to take a little bit of time here to talk about the model consistency check. ASME B31J provides several notes on the scope of all of these calculations and all of this analysis, such as geometrical and component restrictions that was mentioned in a previous slide. If a component in your model is not complying with B31J requirements, AutoPIPE's model consistency check algorithm steps up to the task of alerting the designer of any non-compliance in the model. It is recommended that you review the warnings in the model consistency check report and the design code itself, and make any changes to the component that is not complying where necessary. Now, I would like to warn here that AutoPIPE will still run the analysis for B31J. It will still run the calculations based on the rules and the equations given by B31J, but these results for the model may not be valid. So, review the model consistency check after you're printing your reports, review the code itself, and make sure that it's actually compliant with B31J. All right. For those of you who are still awake, we'll take a look at a simple demonstration of this feature. Luke, before I do that, are there any other questions?
So we just got a question about, can the B31J data be used right now?
B31J data, oh, I see what you're saying. I'm assuming you're referring to if it's valid. If it's valid as of the current code. It is, like I said, it's referenced in certain codes. It's up to your discretion if you want to use it or not in the codes. It can be used right now. The B31J 2008 edition did have testing procedures, like I'd mentioned, for the actual components, and these equations are derived from those. So if you want to think of it as it's been available since 2008. So yes, this data can be used right now as long as it complies to the requirements of B31J. Okay, I'm going to step right into our demonstration here. So
we got a question about, do we have any plans to release this SIF and K calculation engine as a standalone instead of embedded into the code calculations?
Luke, I wouldn't know that offhand. I don't know if there were any plans to release this. Currently it's embedded in AutoPIPE, yes.
I guess AP Dynamics, are you looking to just use this with any code that you prefer? Is that what your question is? We'll wait for a response. You can go ahead with your demo and we'll see if they get their response. Yeah, we just got the response. They're looking to use it with the Canadian code, CSA Z662. So we can look at implementing it for that code. We would just kind of look to have to see, you know, what kind of feasibility that the code scope is, and if that'll work with the Canadian code as well. But yes, we can look at definitely adding it to that code.
Yeah, this is the first of perhaps many steps for B31J. You know, we're getting our feet wet, if you want to think of it that way, in terms of actually implementing this, and we will be broadening the scope as we move along. Right, so let's go into a quick demonstration here. So I have here just a simple sort of distribution model for a process plant, very, very simple. If we open up the general model options dialog here, you can see that we are using B31.3 2012. This is not currently a B31J model, and we have here we have two temperature cases, two pressure and temperature operating conditions, and we've been basically given the task of observing or running the analysis and determining if of course, if the component is under stress in the max P hoop category, as well as both transients ambient to T1, which is 275 degrees, and then a transient ambient to T2, 312 degrees. So I basically set everything else up in this model. We have a welding T here. We're just gonna ignore this checkbox and these inputs here. We also have a reducer. This reducer dialog now has these new ASME B31J sketch 3.1 fields for the arc radius and the length at the small end of the reducer. These are currently disabled. They're only available for B31J. And like I said, this is not B31J as of right now. So I'm just going to run a model consistency check here. There's no errors. Run the analysis. Very simple. Oh yes, and one thing I would note here, some people may not know that we have a nice new ribbon here, which I think is really neat. You know, I actually really enjoy it. It's very user friendly. But we're not talking about that today. We're talking about B31J. So looking at the batch report here, we will look at the code compliance, the results summary, and the analysis summary. And scrolling down here, we can see in the analysis summary, this might take a little, I don't know how long it's going to take for the screen to load here, but you can see that we have ASME B31J is not enabled here for this code compliance. And looking at the code compliance itself, ASME B31J 2012, looking down, we can see that we do have an overstress here of a little over 1,000 psi for the ambient to T2 transient. So if we look here at the results and we go to code stresses, you can see basically where this overstress is happening right here at this intersection. And because of this, of course, looking at the results summary, the system does not satisfy the code requirements. So what would you do as a designer? You would reevaluate the geometry, see if that could be changed in any way, perhaps add a support. But what we're going to do today is we're going to look at we're going to actually activate our B31J analysis for SIF and T flexibility calculations. And to do that, we're just going to go into the Tools tab, open up the General Model Options dialog, and you can see here we have this Use B31J checkbox. We're just going to check it and click OK, and bam, just like that, we're in B31J. So now the model is going to use B31J analysis. And the first thing that pops up here, we have a review consistency check warning messages. Again, I urge that you review these, make sure that your model is actually following B31J, otherwise your results may not be valid. So we're just going to click yes on this and take a look. You can see that we have a list of new warnings here, specifically for B31 Appendix J. And it looks like all of these are for the T. There's crotch radius is less than or equal to 0, and the crotch thickness is less than or equal to 0. If you remember, when we looked at the welding T before, we weren't using the crotch radius or thickness, but B31J requires it. So, and we also have a ratio of crotch thickness to run thickness must be greater than 1.1 for the T's below. These are all provided as notes in B31J, so if you do have the code, you can look back at the code, look up this note, and you'll see why this is happening. So we're just going to change that now. We're going to go into the T, into the welding type here. We're going to set the crotch radius to say 6 inches. This is just an example, and the crotch thickness to say, for example, 2 inches. That's pretty large reinforcement there. And looking at the reducer here, we have some updates for the B31J actually requires now the cone angle. I'm just going to put in a value of 45 degrees here. The arc radius is now required as well for the reducer. We're going to put in a value of 3 inches and a length of let's do a length of the small end as 1 inch.
So we've got a couple questions. One question was he must have missed it where we discussed where this will be available.
Yeah. So, did you want to answer, Luke?
Yeah, I can answer that. So that's going to be, if this is not available currently, it's available in the upcoming release, version 11.0, which, like I was stated earlier, we're trying to get that out in the next month. Our next question is, where do we get the crotch radius?
So crotch radius would be based on the manufacturer. If you're using a specific T component from a manufacturer, they should provide this kind of information, any kind of reinforcements, from what I understand. So this should be provided in your manufacturer's manual or the vendor manual of your T component, if that helps. So we're going to click OK here. You can also review all of this in the input listing here. We have we have a T here, a welding T, and it reflects the actual inputs that we've given AutoPIPE. So before we actually run the analysis, we're going to look at the input listing. I want to show you some of the new reports that are here. So we have the T, the reducer, and the T flexibility. This T flexibility here is a new report. It's being introduced with B31J. It's only available for B31J analysis. We'll click OK and open up the model input listing report. Looking at the title pages here, we can see, scrolling down, we're still using B31.3 2012. We also have a new note here referencing the draft revision that we're looking at. So this will be printed on the title page for every model that's using B31J. Scrolling down here, looking at the T data listing, we can see some new information is provided here from B31J. We're also introducing the torsional SIF. So you can see that this is no longer just a value of 1 like AutoPIPE used to be. It is for the reducer, but for the T, based on the geometry and these inputs, the SIF torsional values are going to be applied to the stress equations. Reducer data listing has new inputs here that reflects the actual input that we've provided, and the T flexibilities data listing report has the flexibility factors. This is something that I mentioned before. It will actually report to you the evaluated flexibility factors after all of the all the calculations are done and the considerations. Right, so let's go ahead and analyze the model here. So we'll click on Analyze. We'll click OK. And just like that, the analysis is done. We're going to pull up the results here. We're going to again look at the code compliance, results summary, and stress summary. And the point that I'm trying to drive home here is that we are now using B31J. It's now enabled, and the code compliance here, the displacement transient from ambient to T2 at this T node here is now under stressed. So using B31J, it provides more realistic stresses, and because of that, you will see more realistic results. So what was previously overstressed is now no longer overstressed. And now the system is satisfied. So that's my demonstration and presentation. I just want to leave you with a few final thoughts. ASME B31J provides more realistic code stresses than the existing B31.1 and B31.3 codes in terms of SIF and K factors. Material and geometric restrictions should be reviewed by the designer prior to accepting these stress results. They will be seen in the model consistency check, and they will be seen in the code themselves. I urge you to review them before actually reporting your results. B31J analysis for B31.1 and B31.3 2012 and later models where the B31J analysis will consider these. So that's, again, as we were talking before, it's sort of an initial step and will later be expanded upon. And finally, just the B31J SIF and flexibility analysis for AutoPIPE can be enabled just as simple as you saw, just a simple checkbox to enable it, and then just modifying a few of the components, the inputs, the geometries, running the analysis and reviewing the results. So that's pretty much it on my presentation on the new AutoPIPE ASME B31J enhancement, again coming out for version 11. And now I guess we leave it open to the floor if there's any other questions that you might have.
So there's some more confusion on the crotch radius. They're asking, they're saying, we got some comments that they don't deal with the pipe manufacturer until they actually purchase the piping and such. But the crotch radius is usually publicized material for standard fittings, and if you have to fabricate the fittings, you're going to have to measure those crotch radiuses yourself. Do you have any other comment on that, Josh?
No. Yeah, unfortunately not. B31J is now considering crotch radius and thickness as value. And it's interesting that you've mentioned that. If it's unknown, I wouldn't know how to actually, what value should be entered in there. So, yeah, that's an interesting one.
We pretty much just would lean on to the definition of the variable within B31J, and you just have to go down that route. Next question is, do you happen to know if B31J can also be used for B31.8 design systems?
Again, it depends on. I didn't actually look at B31.8 or B31.4 or any of the other codes, but the newer codes are beginning to show an option. If I can actually go back here, can I do that? Let me see if I can. There was a reference that I had posted in one of the slides saying, basically saying, alternatively, B31J can be used for SIF analysis. If B31.8 does have that as well, then we will start to look into that and adding that as an option. We will start enabling those checkboxes for those piping codes as they become available, or as they start to accept B31J as an alternative.
The next question is, if you have a corrosion allowance, does that apply on that crotch thickness?
There was no mention of corrosion allowance in B31J, as far as I know, but corrosion allowance would be ideal to consider. It would be a more conservative approach.